Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the 26th lecture of Discrete Structures CSC 102. In the previous lecture we have started counting rules and we have studied introduction, what is basically counting rules. We have also discussed multiplication rule and its applications, and we have started permutations. And due to the shortage of time, permutation of objects around a circle and property of PNR, we haven't discussed these two last topics. So today first we shall discuss these two topics and then we shall start counting rules 2. And in today's lecture, in counting rules 2, we shall discuss counting elements, difference rule, inclusion-exclusion rule, and a very important principle which is pigeonhole principle and generalized pigeonhole principle. So we were discussing in the previous lecture permutations. What is permutation? I have told you that is a permutation is basically how to calculate permutation. The number of permutation of a set with n elements is n factorial, and this is basically how we can arrange the elements of a set. For example, we have discussed the example of a set which contains 3 elements a, b, c. It has 6 permutations because n 3 factorial is 6, and this is the way how we can arrange the elements of the set which contains a, b, c. And I have given you an example of the word computer. How many ways can the letters in the word computer can be arranged in a row? That is basically, if we have these 8 letters C-O-M-P-U-T-E-R, then how many are the ways in which we can arrange these letters? And we have discussed another part B, in which we had fixed CO 2 letters and we had calculated the number of permutations. So this is what we have discussed in the end of previous lecture. Now today, how to calculate permutations of object around a circle, around a square, around a rectangle, or you can say pentagon, anything. That is the objects which are in the form of a circle. For example, if we are given 6 participants in a meeting of diplomats, then they are seated basically in a circular table. Now here the problem is that the circle has no ending point. We don't know its starting point, we don't know its ending point. Then how we can permute the elements or objects which are arranged in the form of a circle? So basically, to calculate the permutations, we suppose that the diplomats which are sitting around the circle, which are 6 participants in that meeting, are A, B, C, D, E, F. So these are the 6 people or diplomats which are sitting in a circular, around the circular table. Now the problem is here is that there is no starting point of the diplomats where we can start. So we have to fix a starting point around a circle. For example, among A, B, C, D, E, F, we can select any one of the diplomat as a starting point. So we have to fix the starting point around a circle and then we can calculate the permutations. So call the diplomats by the letters A, B, C, D, E, F. Since only relative position matters, you can start by any diplomat. So that is, we can fix any any point or any starting diplomat A, B, C, either A, B, C, D, E or F. So here we suppose that the diplomat A is the starting point, and then we place this starting point A anywhere in the circle. That is, if we are given this is a circular table, and these are the seats where these diplomats have to sit. So any of the seat we can mark as the diplomat A, whatever their names, we say them A, B, C, D, E, F. Then this is basically the starting point. Then the remaining diplomats are 1, 2, 3, 4, 5. So the permutations, the number of permutations, that is these diplomats can sit around the circle in 5 factorial ways. That is number of ways how these diplomats can sit around the circle relative to A, because we have to start, we have to fix a starting point, and the other seating arrangements are basically relative to A. So the one is fixed, the remaining are 5 diplomats. Therefore we can say that there are 5 factorial, which is 120, because 5 factorial is basically 5 factorial is equal to 5 into 4 into 3 into 2 into 1. This is 5 4s are 20, 3s are 60, and 62s are 120. So 120 are the ways in which these diplomats can sit around this circular table. So when we have to calculate the permutations around a circle, around a, you can say pentagon, you can say also, if you join these, if you are given 5 people which are seated in this arrangement, then by joining this we can get a pentagon. Again, this doesn't have any starting point where we have to start, so we can say it as a circular arrangement of the objects around a circle. So we can treat such type of figures also arrangements or permutations around a circle. Now the permutations of selected elements. In the previous topic we have discussed permutations. Permutations basically the arrangements of all elements out of a set. For example, in the previous example we have supposed that what are the number of permutations or arrangements of 3 elements. Out of 3 elements we have calculated the number of permutations of the elements of whole set. As in this example, there are 8 letters, and we have to arrange all the 8 letters, and we have to calculate the number of permutations, that is the number of arrangements. How can we write these letters? Now we are going to discuss from a set which contains n elements, and we have to calculate the number of permutations of r elements out of n. Then how we can deal with such type of problems? An r permutation of a set of n elements, that is out of n elements of a set, we have to calculate r elements, arrangements of r elements, that is how we can calculate the permutations of r elements out of n elements of a set. So a permutation of a set of n elements is an ordered selection of r elements taken from the set of n elements. The number of r permutations of a set n elements is denoted by p and r, or you can denote it usually by npr. This is another notation which in some books you will see, this notation NPR, or in the book of Susena you can see this notation P of NR. Now how we can calculate R permutations out of n elements of a set. This is basically an ordered selection. Now the theorem is that how we can calculate this. If n and r are integers such that r is greater than or equal to 1, less than or equal to n, that is r must be less than or equal to n, then the number of R permutations of a set of n elements is given by the formula. This is the formula. First version, it is Pn of R is basically n into n minus 1 and minus 2 up to so on n minus r minus 1. This is basically n minus r minus 1. This we can write it as this, or if we don't write here brackets, this minus, due to this minus here we'll have plus. That is, if we have to calculate P52, then it will be 5 into 4. For example, P of 52, how we can calculate it? This is 5 into 5 minus 1 up to so on. This is basically, here we put, if we put here 5, here we put 2, and 2 minus 1, or this is 5 minus 2 plus 1. What is this? This is basically 5 minus 1, this is 4, and 5 minus 2, 3, plus 1 is 4. So this will come until 4. Here we will stop. So this gives us 5 4s are 20 permutations. So this is how we can calculate the PNR or NPR. Like this we can write it as also NPR. So either we can calculate this, or the equivalent formula of calculating this is this basically, which is P of NR is equal to n factorial over n minus r factorial. Both of these versions will give us the same answer. For example, if we have to calculate the same P of 52 by using this formula, then this will be P of 52, this is 5 factorial over n 5 minus 2 whole factorial. This is basically 5 factorial. We can write it as 5 into 4 into 3 factorial, and this is 3 factorial. Basically here 3 factorial cancel, 5 4s are, we get 20. Again the same answer as we have obtained in by using the first version of the formula. So this is how we can calculate permutation of selected elements. This is basically, if we suppose that we have n elements x1, x2, so on xn, then for the position 1 we have to arrange these the r elements out of these n elements, where n elements are x1, x2, so on up to xn. Then r elements out of these elements will be x1, x2 up to so on xr, and xr plus 1 up to so on up to xn, because xr elements, we suppose these are first r elements here. Then at the position 1 we have n choices, at the position 2 we have n minus 1 choices, at the position 3 we have n minus 2 choices, and so on. At the rth position we have n minus r minus 1 choices. So if we simplify this expression by using the same technique as we have studied the multiplication rule, if we have here n choices, n minus 1, n minus 2, and up to so on, n minus r minus 1, then by using the multiplication rule, all the choices here will be n into n minus 1 into n minus 2 into so on into n minus r minus 1 choices. So this will give us, by using the multiplication rule, this is basically the same as we have discussed the examples and applications in multiplication rule. So by using multiplication rule, we can calculate the arrangements of r elements out of n elements. This is how we have derived the formula of permutations of selected elements. Next, how to evaluate r permutations, that is how to simplify this. I have explained you this, how to evaluate this. For example, if you have p of 5 2, then it is basically 5 factorial over 5 minus 2 factorial, and if we open up 5 factorial, this will give us 5 into 4 into 3 into 2 into 1, and this is basically 3 factorial. 5 minus 2 is 3. 3 factorial can be written as 3 2 1, so this is cancelled out with this and we get 5 4s are 20. Now the B part of this example is how many 4 permutations are there of a set of 7 objects. We have to calculate 4 permutations, means the selected elements are 4 out of 7 elements, 7 objects. So we have to calculate here p of 7 4. So this can be calculated using the both versions of the r permutations formula, which is given in here in the definition of permutations of selected elements. So this you can easily calculate. 7 factorial opens up from 7 6 5 4 3 up to 1, and 7 minus 4 is 3 factorial. So the 3 factorial cancel out with here 3 factorial, and multiplying these 4 integers we get 840. So 840 permutations are there of a set of 7 objects. The next is how many 5 permutations are there of a set of 5 objects. Means here we have to calculate the permutations of all elements of a set. Means 5 permutations out of 5 elements. This will obviously give us p of 5 5, and this we can calculate using the formula 5 factorial over 5 minus 5 factorial. 5 minus 5 factorial is 0 factorial, and I have told you what is 0 factorial. This is basically equal to 1. So 5 factorial is 120. You can calculate 5 factorial. This is 5 into 4 into 3 into 2 into 1. So 5 4 are 20, 23s are 60, 62s are 120. So this is how we can evaluate our permutation using formula. Now another example of the R permutation, which involves the letters of a word. How many different ways can 3 of the letters of the word bytes be chosen and written in a row? Bytes is a letter. It contains 5 alphabets. This is a word which contains 5 alphabets or 5 alphabetical letters, B, Y, T, E, S. Now we have to find the different ways so that 3 out of these 5 letters can be arranged. So we have to calculate 5 p of 5 3, and this is 5 factorial over 5 minus 3 factorial, and this you can easily calculate, which gives us 5 4s are 20, 23s are 60. So there are 60 ways we can arrange 3 letters of the word bytes. The next is how many different ways can this be done if the first letter must be B. So now the first letter B is fixed out of 3 elements. We have 2 letters which are left to be arranged in different ways using permutations. So we have to now arrange two letters. The first letter B is fixed now. In this case we can calculate P of 4 2, because now the first letter is fixed. There are 4 letters in total now, and out of 4 letters we have to calculate number of ways in which 2 letters. First we had 3, now we have 2 letters because 1 is fixed, and the total number of letters, which is 5, is reduced to 4 now, and total number of letters which we have to calculate the different ways is also reduced to 3, from 3 to 2 now. So therefore we have to calculate this now, P of 4 2, because B is fixed now here. Now what are the available letters, which are B, Y, T, E, S, and the positions are basically 2. Here we have to calculate permutations of 2 other letters. So now we have to calculate P of 4 2. P of 4 2 is 4 factorial over 4 minus 2 factorial, which we can simplify easily, which gives us 12 permutations are there if we fix B at the first position. The next is proving a property of P and R. Prove that for all integers n greater than or equal to 2, P of n2 plus P of n1 is equal to n square. So we know the formula of P of n2. This is basically n factorial over n minus 2 factorial. That is, P of n2 is n factorial over n minus 2 factorial. This we can simplify as we open up n factorial up to n minus 2, so that this cancel out with the denominator. So n into n minus 1 into n minus 2 factorial. Now this is cancel out with this n minus 2 factorial in the denominator, and we get n into n minus 1. Now we can simplify this P of n1. P of n1 is basically n factorial over n minus 1 factorial, and we expanded n factorial up to n minus 1 factorial, which is, we can write it as n into n minus 1 factorial, and this is cancelled out with the term in denominator, which is n minus 1 factorial. So we obtain n. Now we take the sum of these two terms. This is basically, the first term is n into n minus 1, the second term is n. If we multiply it inside, we get n square minus n. N is cancelled out with n, and we get this, which is the right hand side of this equation, as we needed to show. So this is how we can prove any property of P and R for any integers n greater than or equal to 2. Now we start counting elements of disjoint sets. Now this is how and what is the application of this topic we'll see in on the next slide, or the example is given here. Suppose now we are given a finite set A equals the union of k distinct mutually disjoint subsets. Now what is distinct, what is mutually disjoint subsets? Distinct mutually disjoint subset means that no two subsets of A have common elements, that is, their intersection is empty. Distinct means no two have elements have same elements, and no two subsets of A have common elements, that is, intersection of any two subsets of A is empty. This is called basically mutually disjoint sets if if we take any two subsets of A, their intersection is phi. Then the number of arrangements, the number of elements in A is basically the number of elements in A1, number of elements in A2, number of elements in AK. Suppose how this definition can be used in some problem of you can say computer science. For example, a computer access password consists of from 1 to 3 letters. Means you fix the password of your computer, which the password, you say that your password is from 1 to 3 words, and it is chosen from the 26 alphabets with repetitions allowed. Repetitions allowed means 2 letters can be same of a password. Means you can fix your password as AAB. This is allowed. You can fix your password simply M. You can fix your password simply AB. That is, password contains either 1 or 2 or 3 letters, and all the letters of the password have been chosen from the 26 alphabets with repetitions allowed. So how many different passwords are possible? Now the set of all passwords basically can be divided into 3 subsets. We suppose that there are 3 subsets, A1, A2, A3. A1 contains all the passwords whose length is 1. That is, in this set the passwords are of only 1 letter. And in the second set, we suppose that the passwords are of length 2. That is, this set contains only those passwords which contains only 2 alphabets. It could be the same letter, it could be different letters, because the repetitions are allowed here. Now in the third set, we suppose that the length of the passwords is 3. That is, the password have any 3 words of the 26 alphabets. For example, we show it in a diagram. This is a set which contains passwords of length 1. This is another set which contains password of length 2, and this is a set which contains password of length 3. Now by the addition rule, the total number of passwords equal the number of passwords of length 1 plus the number of passwords of length 2 plus the number of passwords of length 3. Now we see that how many possible passwords are there of length 1. Since it is restricted that passwords must be chosen from alphabets of alphabets A, B, C, D up to Z, and these are 26 alphabets. Therefore all the possible passwords of length 1 are 26. Now in the second set, the passwords are of length 2 and the repetitions are also allowed. Therefore by using multiplication rule, we can say that the total number of passwords of length 2 is 26 into 26, that is 26 square. And in the third set, the number of passwords of length 3 is basically 26 into 26 into 26, which is 26 cube, because the repetitions are allowed, I remind you this. And now the total number of passwords in all 3 sets is basically, by using this formula, the total number of passwords is basically this plus this plus this. So we add up all these 3 number of elements in these 3 different sets, and we obtain that there are 18,278 possible passwords which can a person fix in his computer by using these conditions. So next, counting the number of integers. This we have already discussed this example, but here we again calculate I shall give you the solution of this example by using this definition, counting elements of disjoint sets. Now here, if we have how many 3-digit integer from 100 to 999, but basically 3-digit integers are those integers which we can write using 3 integers, and these are from 100, that is 100, up to 999 inclusive. Inclusive means both these integers are included in that set. Now we have to determine that how many of these integers are divisible by 5. How many of these integers are divisible by 5? Now we can easily observe that only those integers among these integers are divisible by 5 in which the end letter, the end integer, that is the last integer which comes at the unit place, is either 0 or 5. This is basically in elementary classes you have discussed such type of problems, that is only those integers are divisible by 5 in which the last letter, the last end integer is either 0 or 5. So now systematically we divide this problem into 2 subsets, that is we calculate all the integers from 100 to 999 which have 0 at the end, and then we suppose that there is another set in which all those integers are included in which the end letter is 5. So we suppose there are 2 sets, A1 and A2. A1 set contains all those integers in which the end letter, the end integer is 0, and A2 is the subset of that set A which contains all these integers from 100 to 99. And there are 2 subsets of this set, A1 and A2. A2 contains all those integers in which n integer is 0, and A2 contains all those integers in which n integer is 5. Now the number of integers which are divisible by 5 is basically union of these 2 sets. So we have to calculate A1 union A2, the set of all 3 integers that are divisible by 5, and we have to verify that these 2 sets are also disjoint. Mutually disjoint means their intersection is empty. All the integers which ends with 0 basically are different from the integers which end with 5. So the set A1 cannot contain any of the integer which ends with 5, and set A2, this set cannot contain any of the integer which ends with 0. Therefore these 2 sets must be mutually disjoint, that is their intersection must be empty. So now we have to calculate how many integers contain the set A1 and A2 contains how many integers. First we suppose that we choose the set A1 in which we have to calculate the integers which ends with 0. Now there are 3 integers in basically 3 integer letter, 3 integers, you can say that 3-digit integers in the first set. The first integer cannot be 0 at the first place of 3-digit integers. If the first digit is 0, then for example if we write 090, then it means it is 90. It's not a 3-digit integer. This is basically 2-digit integer. So at first place we must not have 0. So here at the first place we must have either 1, 2, 3, so 4, so on up to 9. So at first place we have 9 choices, that is one of these 9 integers, it may come here at the first place. Now at second place, the second digit of the 3-digit integer may be 0, maybe 1, maybe 2, 3, 4, 5, 6, 7, 8, 9. So here we have at the second place of the 3-digit integer we have 10 choices, and at the last n integer must be 0. So here we have 9 choices, here we have 10 choices. So by using the multiplication rule, we just multiply 9 into 10, and at third digit place we must have only one choice. So if we multiply this 9 into 10, this is 90. So we have 90 integers among 100 to 999, which end with 0. So in first set A1 we must have 90 integers, and using the same reasoning we can calculate that in the set A2 we must have also 90 integers which ends with 5. So the total number of integers which are divisible by 5 in 3-digit integer from 100 to 99, we must have number of integers in A1 plus number of integers in A2, which is 90 plus 90, 180. So 180 integers among the 3-digit integer from 100 to 99 are 180 are those which are divisible by 5. So this is how we can calculate the number of integers by using this counting elements of disjoint sets, using this definition. Now what is the difference rule? If A is a finite set and B is the subset of A, that is, if we have a set A, this is set A, the B is the subset of this set. By using Venn diagram, if we use the Venn diagram, this is the situation in this theorem, in this difference rule. If A is any finite set and B is the subset of A, then number of elements in A minus B is basically number of elements in A minus number of elements in B. So this is, if A is this whole set and B is the subset of this set, then A minus B is basically that set which contains if B contains k elements, A contains n elements, then A minus B contains n minus k elements. This is basically the difference rule. And for example, we have to calculate number of pins. Pins is basically, we have discussed such type of example in the previous lectures. Pin is basically personal identification numbers with repetition. If we wish to form pins using 4 symbols, either letters of the alphabets or digits, means we have discussed this example earlier in the previous lectures. Either letters means alphabets, which are 26 letters of alphabets of ABC, and digits are 10 from 0 to 9. We can use all these letters and symbols to form pins where the repetition of the numbers is allowed. And supposing that letters could be repeated, now suppose that repetition is allowed, how many pins contain repeated symbols? Now we have to calculate that how many pins contain repeated symbols. As I have told you in the previous lecture, we have calculated number of pins with repetition and number of pins with non-repetition, which are not repeating. We had calculated that the number of pins which can be repeated is 36 power 4. This is not 364, but it is 36 power 4. And we have calculated that pins in which the repetition is allowed is this amount, this number, and there are this number of pins in which the repetition is not allowed. Means set A1, for example, contains this type of elements, and the set B, which is a subset of this set. Basically, how we can use this difference rule here, we suppose that the set A is the set which contains the number of pins in which the repetition is allowed, and B is the set of pins, personal identification numbers, in which the repetition is not allowed. So this set must be the subset of this set. So B is subset of A. So we have to calculate now how many are the pins which contains repeated symbols. So if we subtract this number from this number, because in this number there are pins in which the repetition is allowed, and this is the number in which the repetition is not allowed. So to calculate the pins in which the repetition comes, means there must be repetition. You can say how many pins contain repeated symbols. If we subtract this number from this number, we can calculate the number of pins in which there must be repeated symbols. So this we have calculated by using the difference rule here. Now, what is basically the inclusion or exclusion rule? Now, what is inclusion and exclusion rule? This is basically an advanced version of the difference rule, in which there are common elements in the two sets A and B. If we are given three sets A, B and C, and all of these three sets are finite sets, then number of elements in A union B is equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. And the more generalized version of this inclusion-exclusion rule is for three sets A, B, C. If n of A union B union C is equal to n of A plus n of B plus n of C minus n of A intersection B minus n of A intersection C minus n of B intersection C plus n of A intersection B intersection C. So this is basically the more general formula of this formula. Now, for example, if we are given how many integers are from 1 through 1000 are multiple of 3 or multiple of 5. So we have to calculate all those integers which are from 1 to 1000. We have to calculate those integers which are multiple of 3 or multiple of 5. So now we have to divide this in the subsets, and then we shall calculate the number of integers in part A. And in part B, we have to calculate how many integers are there from 1 to 1000 which are neither multiple of 3 nor multiple of 5. Once we have calculated this, then we shall subtract these number of these integers from 1000, and we can calculate the number of these integers which are neither multiple of 3 nor multiple of 5. So to calculate the first part, we suppose that A is the set of integers from 1 through 1000 that are multiple of 3. A is the set which contains multiple of 3, B is the set which contains multiple of 5. Now the total number of integers which are either multiple of 3 or multiple of 5 is basically A union B, and A intersection B contains all those integers which are multiple of 3 and multiple of 5. That is, it contains those elements which are both multiple of 5 and 3. Now we have to calculate the number of elements in each set, in set A, in set B, in set A union B, in set A intersection B. Now, how to calculate the number of multiples from 1 through 1000 which are multiple of 3? If we write from 1 to 999, we can calculate that, we can see that every third, 6th, 9th and so on up to 999, there are 333 integers which are multiple of 3, or you can divide 999 by 3, which is 333. So there are 333 integers which are multiple of 3 from 1 through 1000. Similarly, we can calculate multiple of 5, 1 through 1000. If we write from 1 through 1000 here, now 1000 is divisible by 5. Now there are basically 200 integers which are divisible by 5, which are multiple of 5 from 1 through 1000, because 1000 is, if we divide 1000 by 5, we get 200. So 200 integers are those which are multiple of 5, and all those integers can be written in the form of 5k for some integer k which is from 1 through 200. Now thus there are 200 multiple of 5 and 333 multiple of 3 from 1 through 1000. So we have to calculate this. We have calculated this. We have calculated this. Now this is what we have to calculate. And now we have to calculate the integers which are multiple of both 5 and 3. We calculate the LCM of 5 and 3, which is 15, and now we shall calculate the integers which are multiple of 15. Now there are 66 integers which are multiple of 15 from 1 through 1000, because if we see that if we divide 1000 by 15, we get some 991 or 990 point something. So if we take the integer, this is 990. So no, this is, so if we divide 1000 by 15, we get something 66 point something. So 66 are the integers which are divisible, are multiple of 15. So this is basically 16. Number of integers, number of elements in A intersection B is 66. Number of elements in A 333. Number of elements in B is 200. So simplify this expression, we get this 467. So 467 integers are there from 1 through 1000, which are either multiple of 3 or multiple of 5. Now in the part B, we had to calculate here how many integers from 1 through 1000 are neither multiple of 3 nor multiple of 5. As we can see that, as we can easily observe that there are 1000 integers from 1 through 1000, and 467 integers are multiple of either 3 or 5. Then if we calculate, if we take the difference of these two integers, 1000 minus 467, then 533 are those integers which are neither multiple of 3 nor multiple of 5. So this is how we can calculate the number of integers using this difference rule. Now let's start pigeonhole principle. What is pigeonhole principle? What is its application in computer science, and what is its application in functions, sets? Pigeonhole principle basically tells us that if you have, for example, 5 pigeons and 4 pigeonholes, or 4 you can say cages, 4 cages for 5 pigeons, then at least 2 pigeons must be kept in one pigeonhole or one cage. For example, if you have this is by using this figure, if you have 5 pigeons here and you have 4 cages, 4 cages or 4 pigeonholes, you can say, then at least 2 of the pigeon out of these 5 pigeons must sit or must be closed in 1 cage. That is, for example, 1 is kept in 3rd cage, 4th pigeon is kept in 3rd cage. So these 2 pigeons come in the same pigeonhole or in same cage, and the rest of the pigeons come alone in 1 cage. So in the language of functions, what does it mean? It means that if you have less elements in the codomain set than the domain set, means if the domain set contains n elements and codomain set contains m elements, where m is less than n, then we cannot define a one-to-one function between these 2 sets. This is what Pigeonhole Principle says in the language of functions. So now, what is Pigeonhole Principle? A function from a one finite set to a smaller finite set cannot be one-to-one. What is a one-to-one function? You know it. We have already discussed the one-to-one functions in functions when we have studied functions. So there must be at least 2 elements in the domain that have the same image in the codomain. So this is what the Pigeonhole Principle says in the language of functions. Now, for example, how to apply the Pigeonhole Principle, or we take an example of the Pigeonhole Principle in which we have 2 parts, A part and B part. In A part, it says that in a group of 6 people must there be at least 2 who were born in the same month. In a group of, and the third and the second part of this example is, or we stay here until the first part. In a group of 6 people must there be at least 2 who were born in the same month. Is this necessary? Is this must or not? We have 6 people and months. How many months are there in a year? Basically we have 12 months. So the domain contains 6 elements. For example, we have 6 people, A, B, C, D, E, F. These are 6 people, and there are basically 12 months: January, February, March, April, 1, 2, 3, 4, 5 up to 12. Is this necessary that must there be at least 2 who were born in the same months? So this is not necessary. For example, A is born in January, B is born in March, C is born in February, D is born in September, E is born in October, F is born in July. So this is not necessary. As there are less elements in the domain set and more elements in the codomain set, we can define a one-to-one function between these 2 sets, but by the Pigeonhole Principle. As Pigeonhole Principle says that we cannot define a one-to-one function from a smaller finite set to a larger finite set. Sorry, we cannot define a one-to-one function from a larger finite set to a smaller finite set. This is what Pigeonhole Principle tells us. But here we have the domain set, which is smaller, and codomain set is the larger set. So we cannot apply Pigeonhole Principle here. Now in the second part of this example, in a group of 13 people must there be at least 2 who were born in the same month. And why? Now in a group of 13 people, now we have 13 people and the months are 12. Now here we can apply the Pigeonhole Principle And we can say that by using pigeonhole principle, there must be at least 2 people who were born in the same month, because there are 13 people and 12 months. The domain set is larger and co-domain set is smaller set. So here if we have 13 people, 1 up to 13, and there are 12 months, January, February up to December. So the 12 people are born in the 12 different months, then the 13th people, the 13th person must be born in one of these 12 months. Then we can see that there must be at least 2 people who were born in the same months. So here we can say that by using pigeonhole principle, the 2 people must be born in the same month. So this is what basically the pigeonhole principle says. Now in the second example, in the second part B, among the residents of New York City must there be at least 2 people with the same number of hairs on their heads. Number of residents in New York is a finite set. There may be 500,000. Approximately there are 500,000 people which live in the New York City. So this is basically a finite set which contains 500,000 people. Now in a medical science it has been proven that on a handsome, and you can say that on a young person, the maximum number of hairs on any person's head is basically 300,000. So the codomain set contains basically 300,000 elements, and the domain set contains 500,000 elements, because there are approximately 500,000 people who live in New York City, and on average person, on any person, the maximum number of hairs on the head is 300,000. Now there must be at least 2 people by using pigeonhole principle, as the domain set is the larger set, means it contains more elements than the set in the codomain. So by using pigeonhole principle, there must be at least 2 people who have same number of hairs on their heads. We can say it yes. So for today it's enough. I think we stop here and we summarize here what we have studied today. In the next lecture we shall continue discussing pigeonhole principle, and then we shall discuss the generalized pigeonhole principle here. In today's lecture we have studied counting elements and difference rule, what is basically the inclusion-exclusion rule, and we have started pigeonhole principle. In the next lecture we shall continue discussing pigeonhole principle. We shall discuss some more examples of pigeonhole principles, so that you understand, you can understand completely what is this principle, and then we shall discuss generalized pigeonhole principle. So until the next lecture, Allah Hafiz.